some of the neat properties of the gradient is that just by computing it, we can learn a lot about the surface that we're studying. The first one is that since we know the directional derivative is the gradient dotted with the direction that we're going in, if the gradient itself is the zero vector, that tells me that the directional derivative has to be zero, right? Because the zero vector dotted with anything is zero. This is important. This is super important because think about the idea of a scalar function. When we would take the derivative, when the derivative was equal to zero, we had special behavior, right? We had these idea of critical points, and we could compute special information based upon knowing that. We're going to find that similar behaviors hold when the gradient is the zero vector. And then we also know that the direction of maximum increase, let me say it this way. For a surface, we can take the derivative in any direction, right? That's the idea of the directional derivative. But we might want to ask ourselves, what direction is the maximum? If I were to go in that direction, how could I maximize my change? Well, it turns out that maximum change is in the direction of the gradient. And the reason for that is that if we go back to this piece, that it's the gradient dotted with some sort of unit vector. Well, if it's in the direction of the gradient, so the gradient dotted with itself, you're going to have, think about the dot product, right? It's u dot v is u, magnitude of u times magnitude of v times cosine of the angle between them. But that cosine can only go from -1 to 1, so it maximizes when they're in exactly the same direction, and then when they're in the exact opposite direction, it minimizes, kind of the wrong word, but it's in the opposite of the value. So if I'm thinking about the gradient, I want something that's in the direction of the gradient to maximize that directional derivative. So it turns out that the gradient is there. So if you compute the actual gradient value, not the gradient for the whole surface, but the gradient at that point, that's the direction of maximal increase. So by doing that in sort of a real world scenario, you can kind of snake your way through finding maximal and minimal locations. The way that this is thought of intuitively, often stated, is if you were on some sort of surface and there were little bitty hills and little bitty valleys, or rather usually the way it is, if you're on a mountain and you're trying to get to the top, well, if you just go in a circle and whichever way if you're always pointed in the place with the steepest slope, and you just keep walking in the direction of the steepest slope, even if it changes slightly over the mountain, if you always go in the direction of the steepest, in this case positive slope, then you'll make your way to the top. And the idea of the gradient works the same. But it also has a similar capability. I'm going to jump down to this one, which is the direction of minimum increase is in the negative direction of the gradient. So if the maximal increase is here, well, the negative version goes down, so you still end up with the same overall magnitude on that dot product for the directional derivative, but instead of being a positive value, it's a negative value. So if I were a blind man just trying to get down a mountain, the easiest way to do that, and obviously gravity, I just jump and whatever, but I would look around to try to find the steepest slope downward, and if I keep following the steepest slope downward, I'll find the minimum value. And in fact, there's a method of solving systems of equations and solutions is huge in numerical computing. Actually, a bunch of machine learning algorithms and artificial intelligence are based upon this. It's called gradient descent, or steepest descent algorithm, and fundamentally it operates on these properties for trying to find solutions to problems. So from that, I'll just say that the maximum value of the derivative is just the magnitude of the gradient, and the minimum value is that negative value. And that happens when I'm going in the direction of the gradient or exactly in the opposite direction of the gradient. And those are your five very, very important properties that are used significantly when you're dealing with vectorized information. And finally, I want to point to this. If f is some differentiable function and the gradient is not zero, because if the gradient is zero, there's other properties you got to worry about, then that gradient is normal to a level curve through that point. So what does all that mean? Well, if you go back, you remember what a level curve is. It's the set of all values that have the same output. So I probably should have drawn this beforehand, but I'm going to quick sketch for you. So if I had that, and I have some sort of path, and on this path, the output value is the same, the z output's the same. And if that were a path along a surface, so if this is just some cross section of the surface, then the gradient along that surface is always normal to it. Right? So it's not tangent to it, it's normal to it. And there's a little bit of math there, and it has to do with the chain rule and some things we learned earlier about the way that dot products, when they're zero, can tell us a little bit about the relationship of two normal vectors. It's a lot like what we did when we were finding the tangent vector and the normal vector. But anyway, it's an important result, because what it says is if I can find a path where this thing's always stable, I can know the relationship of the gradient to that path. And that can allow us to kind of construct some coordinate frames and do some interesting mathematics there.